speak a little faster than I normally would, but I will try to speak clearly. Okay? The science plays a leading role in our lives today. Nobody will deny that. The material benefits of science have been enormous. But this comes at a cost at the psychological level, because many things that humanity once believed, science has overturned. We know that the Earth no longer is the center of the universe. We know that humanity is no longer exceptional. We come from other organisms. Science has demythologized a lot of our religious beliefs, not all of them, but many of them. Free will seems to be nonsense in the context of inviolate physical laws. Even the individual sometimes is seen as an illusion, like an onion, where you peel back the layers trying to get to the core, but there's no core there. And in the context of universal laws of physics, virtually everything else besides material is considered to be epiphenomenal. My example of this, my favorite example, comes from my youth when Carl Sagan, a noted American physicist who would interpret science for television audiences, had this long episode of programs called Cosmos. And in one of them was devoted to evolution. Now, Carl Sagan loved dinosaurs as a child, so that he had these beautiful graphics, computer graphics, much earlier than now, of these big dinosaurs fighting with one another, copulating, eating, doing all sorts of things. And his very last sentence in this thing are, these are some of the things that molecules do. Okay? The idea is that you have the molecules, you have the laws, everything else is epiphenomenal. Epiphenomenal means it has no causal reality. It's like the image on a motion picture. It seems to be there, but it has no causality. So that, as a consequence, physics has assumed a position in our society very much like, well, let's go back to the Renaissance. If you remember the great chain of being, like a pyramid that had God at the top, and the Pope, and the bishops, and the priests, and the laity, and the animals, and the minerals, and so forth. Well, today we have this physics is at the top, and then we have chemistry, and thermodynamics, and molecular biology. We have the other sciences, and then at the bottom we have the humanities. And that's sort of the form of our state of knowledge these days. Kaufman has called this the era of physics, the domination of all of science by physics. Now, there are 4 physical laws. They are inviolate, they are never violated, they are ubiquitous, they are everywhere, and they are unceasing. So that many have come to say, well, physical law determines everything. Law determines all. Okay? Now, this isn't just a popular opinion. Some of the best minds of science have advocated this. Nobel laureates, such as Murray Gell-Mann, Steven Weinberg, and David Gross, have said that all causality of origins points downwards, and there is nothing down there but the laws of physics. So here we have a consensus of some of the best minds in all of science. That leads us to ask, is there any alternative to this totalism of physics? Well, I would call upon a little saying by a Polish phenomenologist by the name of Karol Wojtyła, who was talking about the relationship between science and belief. And he said that science should prune belief of superstition. Science should take superstition out of belief. He also said belief should warn science against false absolutes. False absolutes. Well, what does an absolute mean in science, a discipline that professes no absolutes? The rest of my talk, I'm going to try to argue against the totalism of physics by showing that it rests on some false absolutes. And I begin with the 4 major laws of physics. They are strong and weak nuclear forces, Coulombic electrical forces, and gravitation. We also have the thermodynamic laws of conservation of energy and dissipation of energy, but I'm going to put them on the side for the while. Concentrating on the 4 force laws. Okay? Notice that all 4 of these laws are predicated upon material, as if the cause itself emanates from the material. Okay? Gravitation emanates from mass. Coulombic attraction comes from the electrons and the protons, and so forth. Okay, these laws are inviolate. They're everywhere all the time. Now, notice that they are universal and can be stated only in terms of universal variables, okay, such as mass or charge. Very generic universal variables. Anything else that pertains to a particular situation becomes part of what is called the boundary statement, or the boundary specifications, or the boundary conditions. To give you an example, if I want to calculate the pathway of a cannonball, I need to invoke Newton's second law in gravitation. Those are the laws, and that's what we focus on. But I also have to know the muzzle velocity. The cannonball comes out of the muzzle. I have to know the orientation of the cannon, and I have to know the mass of the cannonball. Those are the boundary conditions, boundary specifications. Now, any real problem requires 2 elements. One element is the law, and we always focus on the laws. They are inviolate. The other element that's necessary are the boundary conditions, and we hardly ever talk about them. I'm saying that the boundary conditions must be purely arbitrary. Okay? We have to allow for purely arbitrary boundary conditions. Why? Because if we could find boundary conditions for which the laws were violated, then they would not be universal. So it's true by definition. Okay? The thing is that we normally choose very simple boundary conditions. We take the low-hanging fruit, if you will. So that the boundary conditions become anything that the investigator chooses them to be. Chooses this volition means that intentionality is wrapped up with the boundary value problem and with arbitrariness, contingency, if you will. So the boundary conditions must be contingent. Contingency is a legitimate element of any problem statement. Now notice I use the word contingency and not chance. There's a reason for that. Because when I say the word chance, most people think of blind chance. Chance that is directionless, that is simple, repeatable, and may concern events or objects that are totally indistinguishable. Those are 4 conditions for blind chance. But chance, arbitrary contingency, is not always blind. Consider, for example, the probability of rolling loaded dice that have a bias to them. The idea is that the outcome is arbitrary, but connected with the material configuration, the biased dice, chance is no longer blind. There is a preferential direction towards certain numbers and away from certain other numbers. Repeatable. Okay. There are physicists. There's one physicist in particular, Walter Elsasser, who says that in the biological world we need to be cognizant of unique events, totally unique events that happen once and never more, possibly never more. And you say, how is that possible in a world that's 13.5 billion years old? Well, it just so happens that once you look at the probabilities, when you have more than about 75 distinguishable elements, the combinations among them are greater than the simple events that have ever occurred in the entire history of the universe, okay? So that if they come together by random, chances are in another lifetime or another 20 lifetimes in the universe, they will not occur again. I call such things radical chance. And radical chance happens all the time in ecology because we always have hundreds of organisms or thousands of organisms. And the combinations between these distinguishable organisms is legion. So radical chance has to be added. It's actually more radical than blind chance. Then you have conditional probabilities like loaded dice. And you also have things which Karl Popper calls propensities. After a while, certain results become very regular. They occur most of the time, 95% of the time. And other things can occur, but only rarely. And then, of course, at the very end, you have determinism. So the idea is that we have this entire spectrum of contingency, not just blind chance, and we have to deal with the entire spectrum. Okay. It's erroneous. It's erroneous, I would say, to assume that chance and law act dichotomously. In other words, it's either chance or necessity, as Monod used to put it. That's an important dichotomy that's made that a lot of science rests upon. Okay, I've talked about chance and contingency, and you asked me, well, what about order? There is order in the world after all. Where does it come from? Slide 1, please. Well, okay, order can come from law. Law plays a part in order, obviously. But I would suggest to you that law probably plays less of a part in most explanations than do mutualisms within the living community. And I would like to bring to your attention a dynamic called autocatalysis. And the idea here is we have a process A. It may be contingent, it may be deterministic, it doesn't matter, which, when it occurs, it speeds up, it facilitates a process B, which facilitates process C, which in turn facilitates process A, so that the action of A actually rewards itself, if you will. An example, slide 2, would be, well, yeah, okay, excellent, yeah, would be Utricularia. This is an aquatic weed that is carnivorous, okay? It grows like a feather in the water, and it has these little utricles on it, which if you look under a microscope, have hairs on one end, and there's an opening, and if any organism like this comes along and touches the hairs, it opens it up, and the organism is sucked in, and it closes, and the Utricularia consumes the organism. Next slide. And this Utricularia, the surface of it is the host to periphyte, to algae, small algal cells that attach to the surface, and take advantage of the currents by doing that. It grows faster. The organisms come down to eat the periphyton, and they are eaten by Utricularia, so you establish a cycle. Now, I maintain that autocatalysis plus contingency results in non-mechanical behavior. In particular, one thing is selection. Okay. Now, suppose something happens in B, some arbitrary contingency happens in B, and suppose that event either makes it more sensitive to catalysis by A or makes it a better catalyst of C. If either of those happens, then it will receive more from A. It will be rewarded. Okay? Conversely, suppose there is an event at B that makes it less sensitive to A or a poor catalyst of B, then it will receive less from A. It will be punished, okay? It will have a negative reinforcement. The idea here is that in autocatalysis, there is a preferred direction. That preferred direction is greater autocatalysis. This is an asymmetric situation, okay? Okay, next slide, please. Now, processes A, B, and C do not occur without resources. They need resources, food, energy, and so forth from their environment. Suppose the change in B allows it to get more of its resources and to speed up. Well, that will be rewarded. And conversely, if something happens that makes it can't pull more in, it will be not rewarded. It will be at the end. So that there is a reward for bringing in more into B. But that applies to C and to A as well, so that we have what Isaac Newton calls centripetality. When you have an autocatalytic configuration, there is a tendency over time, as it interacts with contingency, to bring more and more into the autocatalytic loop, usually at the expense of non-participants. Now, an example of such this in ecology would be coral reefs. Coral reefs generally exist in an ocean that is a biological desert. There's very little nutrients and so forth that inhabit the ocean. But the coral reefs tend to sequester, tend to pull in those nutrients and keep it in circulation within the coral reef. This is the growth side of the Darwinian narrative. Because when Darwin first described evolution, he talked about sort of two sides. He says you have this Malthusian growth, okay, and you have natural selection. Growth supplies and Malthusian selection decreases. What has happened over time is that we've forgotten about the growth. It's hard to explain growth, so we put it into the background and we consider it given, and we concentrate everything on natural selection. I think we need to start to rehabilitate the positive side of the Darwinian narrative. The Darwinian narrative, as it now stands, the major attribute, the major event is competition, okay? But centripetality induces competition. Suppose, for example, we have B, and something like D appears, and it is either more sensitive to A or a better catalyst of C. Then the ensuing dynamics will be such that D will dominate, and B will either disappear or fall into the background, so that D replaces B. Notice also that this configuration may be among other configurations, and they are all pulling into themselves, so there's a competition that's induced between them. So what I'm going to say is that centripetality induces competition. Centripetality is prior to competition, is more primitive and more necessary. You cannot have competition anywhere without mutualism at the next level down. Okay? The fact that foxes and coyotes may be competing has to do with this enormous mutualism within the bodies of the competing organisms. Okay? Competition is impossible. This has certain ethical consequences, I might say, because you've probably heard of Darwinian, what's the moral, the Huxley's term. Anyway, it's an inversion of priorities. We have conferences that people go to talk about how cooperation can be possible in a world of competition. But that's inverted because cooperation is more fundamental than competition. Okay, right? So let's step back and take a look at the larger picture. The laws are inviolate. Okay, I'm not saying that laws are violated. They are constraining, but they are not determining. Why not? Well, because of the boundary conditions. We always assume that we can state the boundary conditions, and whenever we state the boundary conditions, we can predict. But nature doesn't realize that we have to state the boundary conditions. They can be contingent, they can be intractable. And as a matter of fact, in ecology, with radical chance, they are intractable. It is impossible to enumerate all of the boundary conditions. Well, that's sort of epistemological, but there's also another problem that Stuart Kaufman has brought up, and that is that we can never state the boundary conditions beforehand because the categories we need to state them still don't exist. And we see that most often in situations called acceptations, which I thank Professor Hilton for. For example, you have something like a cavity within an aquatic organism that was started to develop as a lung to transport gases into the body tissue. But after a while, conditions change, and the organism used that cavity, expanding and contracting it, to regulate its position in the water column. So that an organ that developed for one purpose, suddenly, for reasons that we cannot fully state because they're intractable, is now being used in another direction for another function. Now, notice that that autocatalysis is selecting amongst these compositions. Koichiro Matsuno, I think, called them frozen axes. I don't know if that was Koichiro's word or not, but the idea is that autocatalysis selects among the many contingencies and rejects most of them because it's a stable configuration and can even reproduce itself without DNA. But certain contingencies that help the autocatalysis are incorporated into the dynamic and become part of the internal dynamic. They become a frozen accident, if you will. Now, if this is not particularly clear, I would like to bring in a metaphor for what is going on. A metaphor that was brought about by John Wheeler, John A. Wheeler, a very eminent physicist who thought about these philosophical questions in physics. He was one of the few physicists that really thought bigger, outside the box. Wheeler was worried about constructivism in physics, and Professor Collier has written a paper on this and talked to me about it this morning. The idea that physicists were looking for these new particles. This was back in the middle of the 20th century. And they had this theory that predicted certain particles with spin and flavor and various characteristics. They hadn't seen them yet. So what they did is they went into their cyclotrons and their laboratories, and they created the conditions most likely to see that particle, and they would see the particle, they would discover it, they would write the paper and get the Nobel Prize and whatnot. But the question remains, in Wheeler's mind, did they discover the particle or did they create the particle? Okay, I'd like to perform an acceptation of that. I would like to use Wheeler's ideas as a metaphor for evolution. And the metaphor that Wheeler uses is a parlor game. Okay, the idea is that we've been invited to a dinner, but the dinner is late, and the host or hostess says, please amuse yourself with a game. So we decide we are going to play 20 questions. The idea is we will take someone, Professor L9, send him out of the room, and then we will decide on a word. He will come back, he will ask us questions that we can answer only with yes or no, nothing else, okay? So he goes out of the room, and we close the door, and I say, now, I'm a mean guy, I say, there is no word, okay? There is no word, okay? He's going to come in, and he'll ask the first questions, maybe he'll ask Professor Hilton a question, and he can say yes or no, absolutely, however he feels, yes or no. The second question he asks of Professor Collier, and he said he can say yes or no however he wants to. The only condition on his answer is it cannot contradict his answer. And then he goes around, Professor Ney and everybody else, and this continues until finally he says, a palavra é ecologia, and the only answer is sim. Okay? Now imagine how this looks to him. I mean, we said ecology at the first, and yet, this was self-constructed. Now, why I like this for evolution? Because the laws of physics, I think, correspond to the rules of this game. Okay? There are certain, we cannot violate, we should not violate them, we can, but we should not violate them. And they help the game go orderly. But they do not determine the endpoint. They constrain, but do not determine. What determines the endpoint? It's a dialogue between contingencies. Okay, the questioner, whoever's being asked the question, who's ever's answering the question, is trying to narrow down the possibilities as much as possible. The respondents, everybody else, is trying to broaden it and keep the game going. Okay. Because we have an analogy here with autocatalytic dynamics, which is selective, okay? So all of these contingencies are coming in and it selects and narrows down the possibilities. On the other hand, we have entropy, the second law of thermodynamics that says that things just tend to fall apart and become incoherent and whatnot. This entropy decays the existing configurations, number one, and but it also creates new possibilities. So that there is a Hegelian element to this dialectic in the sense that in order to keep on progressing, autocatalysis needs, at the next level up, needs the contingency. And then vice versa, as things become more complicated, things dissipate more. So that at the next level up, there's mutual necessity. You have conflict at one level and mutual necessity at the longer term. I like the metaphor because what we take home from this is that laws do not determine the path of evolution. They are instrumental, they are constraining, but they do not determine. Every form that we see, every form that we encounter, somewhere is the result of a contingency. Okay? Everything. And that includes physical phenomena as well. Okay? To paraphrase Bertrand Russell, evolution is driven by configurations of contingency. Bertrand Russell knew about centripetality. He didn't call it centripetality. He gave it a terrible name. He called it chemical imperialism, about organisms bringing chemical resources into themselves. But it was the same concept. And he said, this is the drive behind all of evolution. It's a very heterodox, heretical statement because everybody knows that competition is the drive behind all of evolution. Also, I will say that it's not new. Those of you familiar with evolutionary theory know that Stephen Jay Gould, about 15 or 20 years ago while he was still alive, talked about evolution being driven by blind, directionless chance. Okay? And he was referring to a very similar dynamic. But he and I would differ in the sense that he narrows in on blind chance, and I say, no, that's a false dichotomy. You have this spectrum of contingency, much of which is directional, and can even include intentionalities. So, Kaufman says, this is the end of the era of physics. The idea that physics is no longer at the top of the apex, that the other sciences, like ecology, like sociology, and so forth, now have a chance to come forth and elucidate a new dynamics. which, you know, does not violate physics, but is